Hello, good morning, sir. Am I audible?
Yes, sir. You are audible, sir. Thanks for your joining, sir.
Okay, welcome, sir. Sorry, there is some problem. Initially, I have spoken, but you did not hear my voice.
Yes, sir. I'm not able to hear your voice. No problem,
Yes,
sir.
now it's clear? Okay.
Yes, it's clear, sir. So we'll start the event within 2-3 minutes, sir.
Sure, sir.
Yes, thank you, sir.
Sorry.
Sir, shall we start the session, sir?
Yes, Professor, please proceed.
Yes, sir. Thank you, sir. Honorable dignitaries, land delegates, respected faculty members, and my beloved students, very good morning to one and all for the International Conference of Smart Technologies and Applications 2022. I would like to call Ms. Abhinay to deliver the welcome address formally.
Good morning to one and all present here. On behalf of Ramco Institute of Technology, I would like to express my great pleasure in welcoming all of you for the AICTE sponsored International Conference on Smart Technologies and Applications ICSTA 2022, supported by Department of Biotechnology, National Bank for Agriculture and Rural Development, and Builders Association of India. I feel glad to welcome Dr. S. Keriyanahi, Professor and Head, Department of Electronics and Communication Engineering, Ramco Institute of Technology. I would like to extend my warm welcome to all the conference participants, research scholars, faculty members, and students of Ramco Institute of Technology and other institutions. Just before we get started, I would like to express my gratitude to the Chief Guest, Dr. Gunasekharan Thangavel, for accepting our invitation on behalf of Ramco Institute of Technology. I gladly welcome you to this International Conference on Smart Technologies and Applications 2022. We feel very grateful to have you on this great occasion. We welcome you, sir.
Thank you, Abhinay. Now it's time to introduce our chief guest, Dr. Gunasekharan Thangavel, on this great occasion. May I call upon our Deekshana to give brief introduction about our chief guest.
Good morning to one and all present here. It's my privilege to introduce the guest of the day, Dr. Gunasekharan Thangavel. He is currently working as a professor and program director in the Department of Electronics and Telecommunication Engineering at the University of Technology and Applied Sciences, Higher College of Technology, Muscat, Sultanate of Oman. He earned his PhD in Information and Communication Engineering from Anna University in the year 2013 and possesses 20 plus years of experience in teaching as well as research. He completed his Masters in Communication Engineering at the Birla Institute of Technology and Science, Pilani, in the year 2003. He completed his undergraduate degree BE in Electronics and Communication Engineering at Konga Engineering College in the year 2000. He has published more than 35 technical papers in the fields of wireless communications, antenna design, and signal processing. He has filed 3 international patents in 5G and IoT technology. He also acted as a reviewer, chairperson, and delivered special lectures at multiple international and national conferences and workshops. In his experience, he has guided more than 50 BE BTech projects, 15 ME projects, and guided 2 PhD scholars. Dr. Gunasekharan Thangavel is a live member of the professional society bodies of ISTE and IEEE, and also he possesses the highest rank of senior member in IEEE.
Thank you, Deekshana. Ladies and gentlemen, we rarely get this kind of opportunity to listen the words from a great knowledgeable speaker. Yes, I am talking about Dr. Gunasekharan Thangavel. It will be great privilege for us to invite Dr. Gunasekharan Thangavel, speaker of the session, to deliver the keynote address on 5G communication. Sir, the session is over to you, sir. Sir, you can proceed, sir.
Yes, Professor.
Thank you, sir.
Can you able to see my screen? Is it visible?
Yes, sir, it's visible, sir.
Respected dignitaries, audiences of this international conference, my dear faculty colleagues, and student friends, a very good morning to one and all. As the conferences like this will always trigger our mind to learn new technologies, which is going to change the socio-economic relevance of the country as well as the globe. As a part of this conference, I'm very happy to share my keynote address in the field of 5G communication. I'm going to take a simple task on that 5G application, which is called wireless channel models, which is one of the crucial points to be discussed today's era. So these are all my contents. For the next 40-45 minutes, I'm going to deliver about why we need this 5G. Very soon we are going to deploy 6G. You may ask a question, where 4G is there now? Still we obtained the maximum throughput or the promised protocols given by the 4G forum? So far not it. But why we need this 5G and 6G? And what is the need for millimeter wave technologies for 5G? When we are keep on changing the frequency spectrum, is it possible to change the nature? Since the wireless, the channel models, the free space path, everything will be same throughout the year. Is it feasible to change the natural parameters? So it is not possible. So how we are going to adopt the technology to be deployed with the consistent nature of the channel parameters? And what are the different types of channel models we have? And why specifically MIMO channel model has been selected? And what are the various types of MIMO channel models? What is the capacity of this MIMO channel model? What is the significance when compared with the other systems? Then finally, we are going to discuss about the challenges in the RF design. And finally, we'll come to the conclusion. Yes, someone is raised her hand. Yes, ma'am, Helen. Please. Am I audible?
Yes, sir. Yes, sir. You are audible, sir. I
Shall I
thought
proceed?
she may mistakenly raise the hand. I think,
It's
sir.
okay, sir.
Yes, sir. You can do, sir.
So now, let us see why we need 5G technology. As this 1G has been deployed, it is dedicated only for voice communication. The value-added services like internet, email, downloading video, uploading video, all these things are not a part of this 1G. It is only for voice in analog. When it is converted into or deployed into the next generation 2G networks, this analog is slightly changed into digital, but where your voice is still in analog here. But few value-added services have been initiated, and almost 80% of the 1G towers have been replaced with the 2G. When this 2G emerged, so we will move. We have been moving to 3G. It is simply 2G plus 1, which is having some value-added services in terms of data and the higher throughput. But still, we are not happy. There are a lot of bottlenecks to be opened. So we are replacing around 75% of this 2G towers with the 3G, and we move to 4G. This 4G, it is increasing its frequency of operation. The frequency spectrum is around 2.4 gigahertz for band 1. And this 3G, this 4G is simply 3G plus 1. Almost around 70 to 80% of the towers have been replaced. But when we are deploying this 4G to 5G, when we are deploying this 5G, it is not simply like this 3G plus 1 4G. It is not like 4G plus 1 is 5G. Why? This 5G network technology is totally new environment, unlike there is a similarity in all this 2G, 3G, 4G. But this 5G network topology is entirely different in terms of its frequency spectrum as well as the channel coding and modulation methodologies. Why we are moving to this 5G technology? Are you happy with the speed, downloading speed of your 4G as an individual subscriber? What are the two major resources in communication system? As we know, the two major resources in any communication system is power and bandwidth. Why we are paying money to the service providers? We are using their power and the bandwidth. Based on the power and bandwidth, we are going to enhance the signal strength as well as the money. If you download some data, based upon your data, you have to pay. So as a technologist, as an engineer, how you are going to reduce the technical parameters of power and bandwidth in an optimum manner, and how can you able to provide the communication to the affordable cost? That is the question. So there are a lot of promises by this 5G. I'm not going to say everything. I'm going to compare only the latency and the speed. The speed promised by this 5G network is around 10 to 50 gigabits per second theoretically. How can you able to achieve the speed? Without increasing bandwidth, it is not possible, since capacity is function of bandwidth and the signal power. And how you are going to receive or transmit this much amount of speed with your small handheld devices, handsets, like your mobile or tab or something like. And if your channel is cooperating for this particular data rate, that is another question mark. So I'm going to open some ideas in this particular aspect. Then we have designed a few channel models and antennas to support this particular 5G technology. And the delay, the latency end to end, it is 1 millisecond theoretically. It's theoretically, still it is not proved. But this 4G network is typically providing 50 millisecond latency, end to end latency. But this 5G provides 1 millisecond. That's why the applications like smart industry, smart surgery, IoT devices, this 5G network is having its use cases monotonously. So now these two are the major promises. One is with respect to the latency, another one is with respect to the data rate. How this 5G is going to provide such a 10 to 50 gigabits per second data rate? That is due to its high frequency range. So the 5G frequency ranges are divided into two major areas. One is frequency range 1, the another one is frequency range 2, FR1 and FR2. FR1 is in the sub 1 gigahertz bandwidth, which is of 700 megahertz spectrum. It is close to 2G spectrum. Then FR2, this is FR2. FR2 is in the millimeter wave and sub-millimeter wave spectrum. The FR1 is divided into two categories. One is FR1A, the another one is FR1B. So this FR1A, which is of 700 megahertz, why they have chosen this particular 700 megahertz for 5G? The reason, the initial release 3G partnership program, release 15, as explained clearly, the 700 megahertz spectrum is having long wavelengths, and the buildings, long raised structures, trees cannot be the obstacle. These signals are not affected by the obstacles. So it can able to penetrate through these buildings. So we will get a greater coverage range. That is the advantage of the 700 megahertz spectrum. But the problem is the bandwidth of this particular, or the spectrum of this particular FR1A is 700 megahertz, very, very low. So it is not providing a higher data rate. So very low data rate applications, we can select this 700 megahertz spectrum. But as 5G promises to provide data rate in the order of 10 to 50 gigabits per second, so we are moving to the millimeter wave spectrum FR2, which is in the order of 18 gigahertz to 300 gigahertz theoretically. but no RF components are present with this 300 gigahertz. Even we don't have equipment components even from 18 gigahertz to around 28 gigahertz. So this is the limitation due to the device availability, equipment availability. So they are limiting 28 gigahertz in FR 3GPP release number 16. Release 17, the partnership program, release 17, that is the latest, they have been extending this frequency range up to 60 gigahertz. Up to 60 gigahertz. So this is the route map to decide the spectrum of 5G frequencies. This particular FR2 has a higher bandwidth due to its frequency range, but it is a limitation. The limitation here is these signals are short waves, cannot able to penetrate through buildings. So the coverage becomes very, very less. But we can provide a super fast data. The connectivity between the end user equipment and the coverage area is limited. So to balance these two, lower end and the upper end data rate with the coverage area, to balance that, they have introduced FR1B, which is in the order of 6 to 7 gigahertz range, the spectrum. They call it as mid-band. Why they have selected this 6 to 7 gigahertz range? Due to the availability of components. I hope you know this 4 to 6 gigahertz, we call it as C-band. Most of the countries, all the satellite communication, satellite transponders on this particular frequency range. So it is close to that mid-band frequency. So this FR2 have a balance between the data rate as well as the equipment availability. So most of the countries, South Korea, China, have implemented their base stations, 5G base stations with this mid-band. Still research is going on in the channel modeling, channel coding, frame structures, everything to deploy this 5G in this millimeter wave frequencies. There are few base stations deployed that is only for testing purpose, not yet come to the commercialized applications for the subscribers. So now what is the millimeter wave? The millimeter wave, as I said, it starts from 18 gigahertz, which is called sub-millimeter wave, and it can go up to 60 gigahertz as per 3GPP release 17. And the current cellular operation is below 3 gigahertz. We know that it is through 2.4 gigahertz of your LTE and advanced LTE. Still, they are using the concept called a large array antennas at the base station to provide data rate, but they cannot able to provide much data rate more than 1 gigabits per second. What is the reason behind that? Why we have to move this target operating frequency to millimeter wave? These applications forced us to move the frequency spectrum from the 2.4 gigahertz to around 7 or 18 or 60 gigahertz spectrum. The three major use cases of this 5G applications are based upon ultra reliable low latency communication. As I already mentioned, 5G promises to provide 1 millisecond typical latency theoretically. So those applications we can utilize it. Then massive machine type communication. The tiny wirelessly connected sensors, IoT devices, so can communicate each other within the short distance with the minimal amount of power. So here it is a massive machine type communication. Thousands of IoT sensors are connected together like smart cities and smart agricultures. The last one is for the mobile communication, which is enhanced mobile broadband. This is for high speed. That is the one we need the millimeter wave frequencies. So these three are the major areas or use cases where this 5G plays vital role. So we will consider this enhanced mobile broadband. Let us discuss the scenario behind this enhanced mobile broadband for high-speed users, how the channel modeling has been done. So what are the challenges when realizing this millimeter wave for high-speed data rate? As we know the pros and cons of this 5G, the first we will see the challenges. The first one is due to the high path loss. The millimeter wave frequencies are strongly attenuated by the Earth's magnetic field and the high-rise building. And these signals are prone to blockages. And we need a special system design modeling for RF and microwave systems in terms of cost. Cost means, as I already said, in terms of power and bandwidth. So how we are going to mitigate these problems in terms of RF challenges at this millimeter wave frequency. And advantages, as we know, is large bandwidth, higher data rate, flexible deployment. This is one of the challenge for the RF engineers. Integrated access. What is the integration here? Your 5G network is not operating alone, standalone. It is operating with the existing 4G towers, wherever your coverage is needed. So which we call it as non-standalone operation of this 5G. And some of the areas like the short coverages, this millimeter wave frequency, this 5G may act as standalone, that is standalone mode. So that is the flexible deployment. So your device, either it may be a tablet or your computer or your mobile phone, have an ability to switch between these two frequency ranges. So that is flexible deployment. Then high capacity with dense spatial reuse. Instead of putting the word diversity, they are using dense spatial reuse. Then what are the solutions? The solutions I will explain one by one after this next slide. This is intelligent directional beamforming, the tight interworking with the millimeter wave and the 6 to 7 gigahertz spectrum, and how we are going to optimizing the millimeter wave design for mobile communications. So this is the one, as I said, this integrated operation. One channel bandwidth of our LTE or advanced LTE for single carrier is up to 100 megahertz. This is the channel bandwidth, the typical channel bandwidth for the LTE, or you can say advanced LTE. That is your 4G. So here, this particular bandwidth, 100 megahertz bandwidth, is allotted to particular user. Either the user is downloading a data, or he is making a voice call, or you know that this advanced LTE, your voice is also going in terms of packets. Unlike 3G or 2G, here your voice is also going as a packet. So they are allocating this 100 megahertz spectrum, and they are going to add frequency blocks whenever needed. If a user needs some extra bandwidth with affordable cost, they're adding small frequency blocks. So this they call it as carrier aggregation to enhance the data rate, the speed. But there is no proper power management challenges when you add the frequency blocks. We know that bandwidth and gain are always compromised parameters. Any amplifier, any system design, you take the figure of merit, it will be the gain bandwidth product. If you increase the bandwidth, gain has to decrease. So again, there will be a problem with this power management strategies. So that what they have done, they are making this 5G in collaboration with this 4G by combining a 5 LTE channels, each 100 megahertz, it will become at each 20, it will become around 100 megahertz channels. And each 100 megahertz channels, you can able to make a subdivision. So you can increase the bandwidth like this in the non-standalone mode. What is the problem with this? Now the bandwidth is increased from 20 to 100, 100 to 200, 200 to 300. In the base station side, there is no problem. But at the mobile, at the handset side, do you have this dual RF connectivity to service to this particular calls or data? So before taking these things into consideration, how we are going to maintain the multipath in the channel. The second constraint with this power management, we are familiar with the theoretical concept. The first and last stage of any communication system at the receiver side or at the transmitter side is the power amplifiers, which is the next immediate unit with respect to the system. So how we are going to make a challenge towards this particular power amplifiers to operating in its linear region. No power amplifiers, this is the input, this is the output. You know that the power amplifiers are saturating at a particular point. So this saturation we are maintaining up to 1 dB compression point between the linear region to non-linear. So all the power amplifier peak to average power ratio to be maintained within this 1 dB compression point. So this is the another challenge when we are operating your devices in the dual RF connectivity. Now, with this challenges, we are going to talk about the radio channel models. Radio channel models are nothing but the propagation of your electromagnetic waves into the channels, which includes the antenna design and the connectors. So the channel parameter, channel modeling, not only talking about the wireless, it also have to compromise or include the transmitting and receiving antennas as a part of the channel model. Since this 5G, 3G PP has already said that it is going to use the spatial reuse concept. So theoretically, this antenna is also a counterpart of your radio channel up to antenna connector. So now, what are the progression of the channel models? When 1G or any wireless communication, they have started with the free space path loss model. Here the link power budget is the major role to decide the channel models. When 2G comes, you are allowing the user to move. The word mobile is introduced. So we have to taken care of this Doppler shift and the time dispersion models for the 2G. When it is 3G, we have to use the delay spread and frequency selective channel models, like your matched filter concept in digital communication. So when it is 4G, we have been moving to the spatial and angular polarimetric channel models. 4G itself, we are using MIMO, but it is not something like called multi-user MIMO. Here we are using the spatial and angular polarimetric channel models. In 5G, especially this millimeter wave dual mobility dense deployment massive arrays, it is very difficult to create a wide frequency range. So we need a non-stationary spatial consistent channel models. So this 5G is not a single frequency operation. It is having 3 frequencies, 3 bands of operation. So each band, the channel models to be utilized in a different parameters. The consideration of the channel model at this particular sentence will be created with respect to the coexistence of frequency and the geometry of the model. So what are the spatial models we have and what are the requirements we have to discuss about it? So very quickly we can see this. The first one is wide frequency range due to this 5G at the millimeter wave. So these models are maintaining compatibility with the low frequency band at the receiver end, since it has to be operated with the dual band. That is the one. The second one, broad bandwidth. What is the meaning of this broad bandwidth when we come to this new 5G model? And the third one is wide range of scenarios. Either you are applying it to indoor, urban, suburban, rural, high-speed terrains, or your commander vehicles in the electronic warfare. You are allowing both transmitter and receiver to move. In mobile communications, your base station is at the fixed location and mobile, the user is allowed to move. But some of the communications like vehicle to vehicle, double directional, 3-dimensional modeling, like you are allowing both transmitter to move and receiver to move. For these cases, how your channel modeling to be analyzed. The next one is smooth time evolution model. Then spatial consistency, maintaining correlation between the antenna elements in the line of sight and non-line of sight models, and frequency dependency and frequency consistency models for the 5G techniques with respect to the data communication and the high frequency downloads. The one which we are going to concentrate is nothing but this massive MIMO model for the millimeter wave. We are going to consider the non-stationary and stationary models with this spherical wavefront. And the spherical wavefront will be comprised with respect to the electric and magnetic field spectrum to analyze the model consistency. Okay. So this non-stationary models. So the non-stationary models, we are assuming this time varying scenario to be considered with respect to the correlation effect. And as I already mentioned, the scenarios like vehicle-to-vehicle communications, like the military or the commander vehicles, like extra Doppler frequency shift have to be incorporated. And you are allowing the high mobility. You know the flight speed when it is communicating, it is moving around 600 to 800 kilometers per hour. Like your metro or electric trains, you are providing Wi-Fi, something else, it is moving with 500 kilometers per hour. So we have to give a channel model including this high mobility constraints. So this is the recent advancement in massive MIMO channel models based on the references. What are the channel they are going to utilize to calculate the characteristics or to analyze the characteristics of the MIMO channels with the different applications? We have selected the stochastic models with a spatial correlation domain. Okay, so based upon that model, what are the antennas? Either it is an array or it is MIMO or it may be something like a mode antennas, multi-mode antennas to be suitable to compensate these two effects. As we took this wide sense stationary uncorrelated scattering condition, that is the assumption. What is this uncorrelated condition? We will simulate something. I will show you the uncorrelated conditional model. And what are the system functions we are going to consider? The system functions are, as like your digital communication filtering model, we have to take frequency domain models and time domain models. So we know the frequency domain model to time domain and time domain model to frequency domain. We have to go with the Fourier transformation. Either it may be a fast Fourier transform or it may be a DFT, direct Fourier transform, depends on your requirement. So we start with the impulse response model. What is impulse response? Impulse response is nothing but the response of your filter in the ideal condition. What are the ideal conditions you are going to make? So we know there are two ideal channels for the wireless communication. One is independent and identically distributed channel matrix. So we have to consider this independent and identically distributed channel matrix, IID. You may consider the channel maybe a Rayleigh, Raysian, Okumara, Nagakami, or Gaussian, whatever may be. But the ideal model random entries are calculated with respect to the independent and identically distributed parameters. That is the first mathematical parameter you have to consider. And all the models are 3D models for the MIMO. A space time, one is space, another one is time, another one is with respect to the frequency. So how can you able to take the transfer function? We know any system in signals and system or something else we have studied, this is the input in time domain and frequency domain, and this is the impulse response. So either you are taking the transfer function is nothing but output by input, which is equal to the impulse response, or you can take the direct impulse response models by selecting this HF omega. So we took two parameters. One is with respect to the correlation matrix in spatial dimension with respect to frequency coherence. So we took a stochastic model, that stochastic model with correlated antenna elements to model the 5G antenna elements. Then let us look into the basic constraint. What determines the capacity of network? The upper bound of any wireless capacity is determined by the Shannon's channel information capacity theorem. This is a very fundamental theorem. Look into this theorem in a different way. You want to increase the capacity. There are two constraints. You have to either increase the bandwidth. Up to a certain level, you can increase your signal power. You cannot go maximum signal power since noise also has to be added along with the system. And there is a scale, this Shannon-Hartley used for this information capacity is logarithmic scale. We know the disadvantage, or sometimes it is advantages in communication system, sometimes it is disadvantages. What is the disadvantage in capacity? If I want to take a capacity between 10 to 1 lakh, you take a logarithmic scale. Basically, the base is 2 for digital, but I'm taking for convenience, it is logarithmic of base 10. So log 10 becomes 1, log 1 lakh base 10 becomes 5. We know that. So here it will become compressed. So capacity increases with respect to a logarithmic scale, not a linear scale. So 5G promises to provide a huge data rate for the given bandwidth and given signal power without modifications in the major bandwidth, only using this MIMO concept. So MIMO concept is nothing but using M transmitting antenna or N transmitting antenna with M receiving antenna. We are going to replace this logarithmic scale into a linear scale. That linear scale will be spatial diversity scaling up M cross N or N cross M. If you increase number of antenna elements without touching the bandwidth and SNR, capacity gets increased. So we are going to slightly modify this channel information capacity theorem, okay, the channel capacity theorem, by making the movement of this logarithmic scale into linear scale. That we call it as massive MIMO beamforming. So the signal power is directed to the intended mobile user instead of your switched beam architectures available with this 4G and 5G, 4G and 3G systems. So we are directing the power to the intended user, the dedicated power to the intended user. So it will be compromised. You can able to break the beam and track a single beam with respect to the user. So that we call it as beamforming. That is another strategy. So our aim is now how the capacity growing with respect to a logarithmic scale is converted into a linear scale by means of this MIMO. So as we have done with a multi-correlation simulation, when this number of antenna elements are increased from 4 to 8 for the given SNR, you can check the capacity is increasing linearly, growing linearly for the given SNR instead of logarithmic scale due to the MIMO. So MIMO proves that the channel capacity law, instead of growing the capacity in logarithmic manner, it will be growing in a linear manner. So one of the problem in the mathematical complexity of this logarithmic scale is converted into linear scale. Now comes to the channel modeling. All the channel models available in the current wireless scenario, relay, Gaussian, or whatever may be, they are assuming the capacity, channel capacity is logarithmic scale capacity. Now you have converted that logarithmic into MIMO. So you have to make your own channel models based on your application. That is the challenge here. So as we have been proving that the capacity of MIMO systems are growing linearly with respect to the number of antenna elements for the given SNR. Okay, you can take any point, you can check, it will be increasing linearly with respect to the number of antenna elements. So now let us come to the channel modeling. Now we proved that capacity is increasing linearly, so logarithmic scale is converted into a linear scale. Now how you are going to modify your channel modeling? So you have to check the channel. Whenever you are coming to channel, the electric field and magnetic field behavior of your channel enter into the picture. Since the energy transmitted in the azimuth spectrum, for example, your magnetic field, which is varying from 0 to 2 pi radiant, and for elevation, zenith spectrum is varying from 0 to pi. We know that this is a fundamental concept in the antenna. So now how you are going to calculate the power azimuth spectrum? So we need a power delay, strong power delay profile to characterize the channel in terms of its Doppler power spectrum. So you are connecting antennas like a MIMO, number of in the same system, in the same mobile phone or your base station, you have a MIMO system like this for transmit and receive modes. One is for transmit mode, another one is for the receive mode. And you consider there is another MIMO model like, so here the channel have to be identified as a multipath channel. The problem with this multipath channel, how you are going to distribute the power azimuth spectrum. So the waves arriving at each receiving antenna at a span of mean arrival angle. So using this concept, you consider we considered three different power distribution. One is uniform, another one is Gaussian, the third one is Laplacian. And we have studied the working principle of this MIMO based upon the azimuth power distribution. So how this multipath scenario is affected when you increase the number of antenna elements from 2 cross 2 to 4 cross 4, 4 cross 4 to 16 cross 16, how this will be affecting the transmitted data in the channel. So we consider two categories of the solution. One is spatial diversity, another one is spatial multiplexing, which is there for quite long time, 20-15 years before. There is a MIMO concept introduced in some of the low density applications. The spatial diversity concept is not new. So, but we are making the spatial diversity concept for the MIMO channels, which is correlation-based stochastic model. There are two mathematical modeling are famous in this one. One is geometry-based stochastic model, stochastic channel model. Another one is non-geometry-based stochastic channel model. So here we will consider the geometry-based first, then we will correlate the space-time codes with the transmit and receive antennas. The problem is the correlation among the antenna elements. The autocorrelation between the antenna elements will affect the multipath. Since these antennas are co-located, these multipath will interfere each other. What is the amount of interference when you consider this millimeter wave frequency? There are a lot of studies available for the frequency ranges starts from 700 megahertz to around 10-12 gigahertz. When you moving from 18 gigahertz to 60 gigahertz sub-millimeter wave to millimeter wave frequencies, how you are going to make the channel model in an ideal way to produce an uncorrelated channel without affecting the multipath. If the multipath is affected, the data rate is also to be reduced. So we are calculating the effective cross correlation between the antenna elements. As the literature states, previously they are using S-parameter approximation proposed by the Smith. It is not very acceptable in the real environment. What is the reason behind that? The S-parameter model is an isotropic assumption model, meaning if you have a transmitting antenna here, we assume that it will be radiating in all directions. But in the beam forming in MIMO, we are directing the power to the intended user. So this should not be, or this may not be a suitable model for this real-time environment. So we have to move with this effective cross correlation for the far field parameters of the antenna. So what are the far field parameters we are going to consider when you are employing diversity, when you are employing the antenna configuration to analyze the correlation effect? One of the stochastic model is called the simplest model, which is called the Kronecker model. There are two assumptions which are all considered in this Kronecker. The first assumption, the receive and the transmit antennas are completely decoupled. There is no relation between the transmit and receiving antenna, but practically it is not feasible. But we are assuming that the correlation properties of the transmit and receivers are completely decoupled, meaning analysis will be easier at the transmit end as well as the receiving end. So we can clearly study the channel parameters. That is the first one. And the second assumption, it is called independent array optimization. We in Kronecker, we won't call this as MIMO. It is a transmitter side for 4x4. This is at the receive side. We call it as array. If you combine together, it is called as MIMO. But we are separately analyzing the transmitter and receiver to know the channel characteristics. So we call this model, particular model is independent array optimization technique. So what is this independent array optimization? Transmit array is separately analyzed, receive array is separately analyzed. But in MIMO, it is not possible. But this Kronecker allows us to make this impulse response of the channel as to analyze the correlation model in this way. So the basic equation of this Kronecker is the autocorrelation matrix of the receive antenna, autocorrelation matrix of the transmit antenna, and there is an impulse response HF omega. As I already mentioned, there are two methods. Either you can go with the impulse response, or you can analyze with respect to the transfer function. We started to analyze with respect to the impulse response of the random entry model. So the HF omega, initially we have assumed IID random entries. Based on the number of antenna elements and the power what we fed to the antenna, that is the pointing power, which is equal to, we know the average spectrum based upon the antenna selection 1/2 into E cross H star. So we selected two antennas, one is the microstrip array, another one is the dipole array, and we have evaluated this Kronecker matrix for the two arrays. Initially, this identically independent and identically distributed random entries have been selected. Now we understood why Kronoker has taken this word independent, since he has to put this impulse response of the channel initially with respect to IID random entries. So this is the one of the major correlation matrix in the mathematical modeling we have to carefully analyze. There are two major problems will come when you are running this code in MATLAB. There is some autocorrelation simulation available in the Kronoker model already in the internet. But when you are selecting the model, you have to check the power azimuth spectrum, what they are calculating inside it, and you have to write your own code for the power spectrum analysis. Otherwise, the autocorrelation matrices should not match the dimensions in the transmitter and the receiver array, then your code will not get the correct result. So that the optimization parameter, we recommend we have to write our own code instead of using the codes, autocorrelation codes available in the internet. So based on these assumptions, we have evaluated the MIMO system capacity in two environments. The first environment, we minimize the for loop by considering the array distance, that is element spacing, is up to 0.4 lambda for providing less correlation effect. This is based on the Balanis approach in the year 1967. There is a paper by Balanis. He quoted that the antenna element spacing is 0.5 lambda and greater than 0.5 lambda, we can able to provide such a beam pattern without any grating lobes. That time they are not using the word correlation, they are using grating lobes. That is the unwanted maxima in the other directions. The same concept if you utilize in the cross correlation matrix, you have to keep with 0.5 lambda, then the spacing of your lambda is very, very minimum. Why? You are in the 18 gigahertz. 18 gigahertz frequency will always lead very, very short wavelength. So the gap between or the spacing between the antenna elements are very, very small. Antennas are reciprocal device. So if one antenna transmits, other receives the azimuthal power, so that you need a large correlation analysis at the user equipment side. In the base station side, this problem is not a matter, such a serious problem, since we have enormous space in the base station. But when it comes to the user equipment like mobile or your tab or laptop or some of the other high-speed drones or vehicles, the space is a problem. So that we have an effective solution to correlate, reduce this effective correlation without compromising the spacing between the antenna elements and also the capacity. So for that, we have been evaluating the spatial correlation, including the antenna parameters in the channel. What are the antenna parameters we are including in the power azimuthal spectrum to calculating the spatial correlation? The first one is the total power azimuth distribution in the channel. Initially, we assumed this is uniform distribution, but actually no channel is providing uniform distribution. So some of the channel provide Rayleigh, some of the channel provide Raysian. So we have to select which channel you are going. Either your channel may be frequency flat channel, or it may be a maximally flat channel, or your channel may be Dopplerly most affected channel. Based upon the application, you can select. We selected two channels. One is frequency flat channel, another one is frequency selective channel. So we have considered the Nagakami for some of the applications in the IoT internet applications, like the short distance maximum data rate applications at the millimeter wave frequency. So we assumed this power spectrum distribution is as a Gaussian distribution, since it is giving only a local minima. We don't want the global minima to cover the large geographical area. And the second parameter which we have considered here is the power azimuthal spectrum with respect to the maximum radiated power. So we calculated the maximum radiated power with respect to the Poynting's theorem. So this mean power is simulated. As I already told you, we took two antenna. One antenna is for the array with respect to microstrip. Another antenna is with respect to dipole. So we calculated the electric field azimuth radiated in this theta phi plane. Then we evaluated the spatial correlation matrix rho for a 4x4 antenna. For a 4x4 antenna. This 4 transmitting antenna independently optimized. This 4 receiving antenna is independently optimized. So we will get 16 random entries in the channel matrix originally. So let us see what are the 16 random entries and how we calculated the spatial correlation for the 16 random entries with respect to the Kronecker product. K is equal to 1 by root of P1, P2, P1 at the transmitter side, P2 at the receiver side. Then we evaluated the normal cavity model microstrip analysis to identify the power azimuthal spectrum, and the joint power spectral density in the elevation and the azimuthal angle is given by P theta into P phi. Then we calculated the minimum angle of arrival at the azimuth plane is at 45 degree. Then later on we have changed the procedure and the simulation with respect to various values of AS and ES with respect to the spatial correlation. So we studied this 4x4 MIMO system with the autocorrelation matrix, the eigenvalues with respect to the impulse response statistics. This is the spacing between the antenna elements are given sufficient to provide a less correlation or zero correlation. You can check the correlation between antenna element 1 to 2. So what we have done, we consider the 4x4. So the first antenna is excited. The second antenna, third antenna, fourth antenna is ideal. You can check the distance between 1 and 2, 1 and 3, 1 and 4. So 1 and 2 are more close to each other. 1 and 3 and 1 and 4 are far away. So at this excitation, we have calculated the first random entry in the matrix, channel matrix. Then what we have done, we took the second as the element. Here, care must be taken. If you take the second element is the excited, 1 and 2, then 2 and 3 are more close. So the second random entry to be incorporated these two parameters. Like this, we have evaluated the channel matrix for each and every values of 4 elements, and we calculated. We can able to prove that there is no correlation if you might be having a spatial correlations with respect to 0.4 lambda to 0.8 lambda. Then if you reduce the spatial correlation, that is reduce the spacing between the antenna elements, the same constraint, 1 is excited, remaining 2, 3, 4 are silent. So that is the case, 1 and 2 are more closely spaced, and then it is providing a strong correlation effect. The multipath will be reduced. So see how many multipath we have, 1, 2, 3 multipath instead of 4 multipath. So the capacity is decreased. So how can you able to solve this problem? So the solution will be very easy. What we have done, we have changed the antenna element spacing for various values of this azimuth and elevation spectrum by changing the distribution of the channel matrix. Then the spatial correlation is evaluated. We found that at AS and ES of 80 degree, at not 90 degree, at 80 degree, this microstrip and dipole antennas, the spatial correlation will be very much closer or very much closer to 0 at this 0.75 lambda distance. So this is the optimal distance to provide the spatial correlation for microstrip and dipole arrays when it is utilized in the user equipment, in the handsets. And for that particular capacity, for particular spatial correlation, we have kept all 4x4 antennas. We have developed around 17 sets of antenna elements, and we have tested the mean capacity after simulating the capacity with respect to SNR. Again, we proved this MIMO as giving a linear increase in capacity with respect to SNR. But there are two limitations here. I will tell you what are the limitations when we modify this particular, or when we implement this model into a realistic model. So once we have completed this Kronecker array model with 4x4 elements, we have tested this with the circular patch with multimode. That is, we can call it as an antenna operating at 2-3 different frequencies by changing its feeding locations and the diversity. So the channel, again, this is the microstrip geometry with the 2 coaxial feeds. And the channel, what we have assumed is again the Kronecker, but the model has to be analyzed only with respect to the azimuthal spectrum, not with the elevation angle. Why? Here, the transmitter side we have array, receiver side we have multimode. Like that, we have 4 constraints or 4 conditions to simulate this channel model. What we have done, array at the transmitter, array at the receiver. Then array means, you know that it is the array, uniform linear array. And here one antenna with multimode, how the channel behaves. So we identified the channel matrix with this 4 category. The first category is when antenna arrays are at the transmitter and the receiver, first case. Second case, multimode at the transmit, array at the receive. Third case, both transmit and receive is with multimode. So like that we have analyzed and we compared with the various distances of the transmit and receive antenna. One is kept at the base station side, so with the 2 lambda distance. Another is at the user equipment side, so which is with respect to 0.5 lambda distance. And we calculated this radius of the scatter disk to the transmit receive with 0.5 lambda. So this is the multimode channel capacity. The first one is the theoretical IID capacity. And you can check in both transmit and receive or array, we have almost 12 bits per second per hertz is the capacity. When you have modes at transmit and receive, this is the last case. And this case, modes at transmit and array in the receiver, you can see the difference in the bandwidth. Difference in the bitrate for the given bandwidth. So it is only around 2 to 3 bits per second per hertz. So you can able to clearly state that instead of using arrays, we can design multimode antennas for the handsets, for the applications in the millimeter wave and submillimeter wave. Will avoid the problem of maintaining the spatial correlation matrices in the channel to maintain the capacity consistently. So this is the inference as I already mentioned. So thus employing multimode is an intrinsic solution for the user equipment compared with the traditional antennas. Now let us come to the RF antenna and testing. Once you have done the simulation with this 5G toolboxes in MATLAB or other certain characteristics to be analyzed with respect to the real-time software tools, we have tested these antennas after fabricating the antennas in our laboratory with the different frame rates and higher throughputs. But at a certain point of time, we don't have network analyzers or we don't have resources to test these antennas operating at the 56 gigahertz and 60 gigahertz frequencies. So we have been tied up with the Samir, or we have been in touch with the other research institutes which have that facilities. So that time we have conducted this Samir Center. They have provided a lot of test beds to us, and we have tested around 12 to 13 antenna sets here with array and multimode. This is the testing requirement for the test bed creation. We need a dual polarized antenna, and all the antennas must be having a high isolation. And we have to develop a MIMO and massive MIMO setup. And the RAN, radio access network, this is very, very important when we are modeling the channel for the particular applications. Then how you are going to integrate your RF front end. As we already mentioned, this RF integration is the crucial step when you are operating this 4G and 5G in the integrated backhaul approach. And the user equipment antenna development is another challenging task for the applications in the millimeter wave frequencies. Nowadays, the mobile phones are foldable phones. So that is the case. Making user equipment antennas is very flexible. So we can go with some of the fractal antenna designs instead of this conventional or traditional cavity-based antenna structures like microstrip. So this is the requirements for the millimeter wave RF. Here, the word beam steering is a question mark in the channel to direct the intended radiated power to the direct users. So nowadays, this SAW antennas are famous, substrate integrated waveguide based antennas. These antennas are helping us at this millimeter wave frequencies. So we have started a small analysis of this substrate integrated waveguides to analyze the channel modeling. So these are all some of the design challenges. There is no components available at 28 gigahertz and more than that. Then we have to comply with the 3GPP release 15, 16, 17 in terms of SCR. You know that what is that? Specific absorption rate of the human body. That is this EMI, EMC challenges. That is one of the major problem or challenge when we are going to design the systems. So at the part of this 3GPP compliance, what is the effective isotropic radiated power they are mentioning in the total electric field and magnetic field conditions, and how you are going to integrate your RF antennas with the modules of your power amplifier, switches, other equipments, other digital components and analog integrator circuits inside it. That is the another challenge. The next one, as we already mentioned, the antenna element design, element spacing, cross polarization, feeding techniques. Usually an antenna engineer always keep these four parameters in mind, but these four parameters not only with respect to your antenna domain, you have to check these things with your channel correlation matrices. That is the challenge. There are artificial intelligence, there are many optimization techniques are available with the antenna tools itself, even your CST, HFSS, many channel models, many software tools are available in market, CST, Micro Studio like. Most of the models are nowadays allowing us to simulate and emulate. We know what is emulation. We have some hardware. That hardware to be interfaced with your simulation environment, you can start your testing. So instead of doing simulation alone, we can able to do emulation. That will help us an insight to analyze the channel models for the future wireless networks. So these are all some of the in general challenges. What is in general? When you are selecting PCB substrate, usually we are selecting FR4. It is readily available in the market. The problem with this one is we cannot go with multi-layer structures. Multi-layer structures up to 10 layer, 15 layer, 14 layers are available in the simulation matrices. When it is given to real-time environment, we cannot able to do that. So care must be taken to select the multi-layer designs, multi-layer substrate materials. With the thin substrate, we can go with the composite materials like, and also PCB R2 to EM simulation. So first you have to design the antenna and the PCB, then again you test with the simulation parameters, the simulation time will go. For us, we created two test beds, one for 2x2, another one is for 4x4. You know how much time taken for this one? It is almost 72 hours. And this 4x4, it makes us 96 to 102 hours. So the simulation time is also another matter. We took only 100 frequency points at a frequency rate of 18 to 28 gigahertz. And the center frequency we selected is 21 gigahertz. So these many challenges have to be crossed when you go with the selection of the substrate materials for your antenna. These are all some of the design challenges usually a design engineer has to face. The major environment we have to check is electrostatic discharge. Whenever you are dealing with the PCBs or high voltage structures, high frequency values, this electrostatic discharge. I hope we have come to the conclusion stage. So as 5G is promising us to provide a large data rate, higher throughput, everything. At the meantime, with major advancements, these are challenges in terms of equipment as well as the innovative solutions may create an appropriate channel models to solve these bottlenecks to provide a sufficient characteristics to the end user with a lot of use cases. Still, there are innovations, research required in the frame structure, multiple access techniques, channel coding, spectrum and architecture, network planning, frequency allocation, everything have to be done in a proper way to analyze this particular MIMO channels and MIMO with the 5G applications. So before deploying this 5G, we need to do all these things when it is converged to the total system model for the socio-economic development. These are all some of the references which I have been taken. Then and there I have put the references. If you have any queries, you can ask me.
Yes, sir. Thank you, sir. Thank you for your session, sir. Participants, may be having queries, means please unmute your mic or type your questions through chat box. Sir, one question came from Monica. We keep hearing that 5G will require millions of small cells. What is that, sir?
Pardon, sir?
5G will require millions of small cells. Is it so?
I already mentioned, yes, it is true.
Yes.
As this 5G millimeter wave frequencies, we know that the millimeter wave frequencies are having less coverage with high or super fast data. If you have less coverage, you need to place many transmitting antennas, many repeaters to cover large geographical areas. So we need a large number of smaller cells to cover the area and provide the service to the end user. Obviously, we need a smaller cells only due to the effect of the channel at this particular frequencies. That's why channel models to be properly utilized when you are installing a new tower at millimeter wave frequencies, you have to check the power azimuth spectrum with respect to the angle of arrival, since you are directing the beam to the one user, not like your traditional 4G system. So obviously you need 10 or 15 to cover at least 3 kilometers. That's why the deployment is still a question mark in millimeter wave frequencies for the individual subscriber. But industries like small scale industries or your military applications, it is dedicated applications like smart agriculture. You are not covering a large geographical area. It is only limited with the geography, so that it is very easy to implement this IoT applications. That's why initially this ITUT, International Telecommunication Union, telecommunication sector has given permission to enable the short distance wireless communications in the IoT applications, smart city, smart home with limited geographical areas.
Yes, sir. Thank you. Sir, one more question from Rajalakshmi. Actually, it is a society-based safety issues question. That we lost various bad species and also which interferes human health due to the frequency. So it is really necessary to implement 5G network, or else we are having another technology to adapt it.
It's an excellent question. As I already mentioned, as the one of the design challenges as an electronics engineer, as an antenna design engineer we face, we are unable to compliance with the 3GPP effectively with respect to EIRP, effective isotropic radiated power. They mentioned the effective isotropic radiated power for 20 scatterer is only 10 dB. But when you design a 4x4 antenna, you can check your antenna parameters for a small coverage area. It is coming around 48 dB. So we have to be comply with the 3GPP standards while designing and simulation itself, and your mathematical models should be strongly supporting by compromising many parameters to provide that EIRP. G frequencies either to be operating at a higher level of power or lower level of power. These EMI-EMC compromises must be analyzed. I have a question for Dr. Rajalakshmi. Please don't mistake me. When you are buying your 3G or 4G phones, they have given a small papers or 4 or 5 papers as a small booklet. Have you gone through it? If you might have gone study those 4 pages, you might have heard the word SAR, specific absorption rate of that electromagnetic wave, watts per kilogram. If you are 70 kg body, I am a 70 kg body, how much electromagnetic power will penetrate to my body is 1 millimeter depth, how much it will go, 10 millimeter depth, how much it will go. Like that, they have given the specific absorption rate. So there is no strong evidences stating that these electromagnetic powers creating harmful effect to the human body with the existing frequency. That's why this ITUT and WHO has strongly collaborating all these things, and this 4G spectrum has been released in the year 2011. But this 5G, you can say that the frequency range are keep on increasing to 18 to 20, 20 to 60 gigahertz ranges. Definitely these penetrations will go 1 millimeter to 10 millimeter. So it may go to the intervein. So care must be taken to incorporate these frequencies in the handset. Even though nowadays the medical field, this bioelectromagnetics, people are telling that don't keep the mobile phone near to the born child or the child which is of 3 months, since their brain size and their organs, the internal human body organs are very, very minimum. When the wavelength of this electromagnetic wave is comparable with the human body, like the fingers or any other thing, instead of penetration, the electromagnetic wave got radiated. So we know two constraints. When the physical length is comparable with the electrical length, the signals are transmitted. When the physical length is lesser than the electrical length, the energy is radiated. So in radiated mode, it will create lot of heat. Transmission mode, there is no heat. When you speak a cell phone like this for 10-15 minutes, when you remove it, you can feel a heat. Reason, the structure is like a circle. You know, microwave oven, how it is rotating and producing heat, it is rotating circularly. We know that rather than a straight conductor, bent conductor radiates more and absorbs more also. Like your kidney, liver, heart, everything is brain, everything is going like that. That's why they are telling that hands-free communication is something better. So we can discuss this one in a massive manner, but as an antenna designer, according to my antenna, it is not providing any issues with this specific absorption rate. But this question to be properly addressed by research and development group have to be compromised with respect to the frequency and the power before deploying the 5G completely. Thank you for asking this question.
Thank you, sir. Thank you.
Usually I ask this question to the presenter always when I'm attending a conference or seminar.
Very good question and very good answer from both of you, sir. Okay, any more questions from other participants? Any more questions? And one more thing, sir. What about the antenna manufacturing company? Why it is still low in India when compared with other countries, Europe? Is there any issues, challenges faced by Indians?
Sir, who said there is no antenna companies available in India? There are a lot of effective antenna manufacturing companies available in India. You know, for NASA also we are giving antennas.
Oh, from okay.
You know, IIT Bombay, Dr. Girish Kumar.
No, don't know, sir.
Bharati Bhatt from IIT Delhi.
Okay.
Dr. Raghavan, yes, Raghavan from NIT Trichy.
Yeah, well known.
So those people have their own antenna design manufacturing centers, and most of their products are used in Kargil. You know, this Professor Kaul and Bharati Bhatt. So they have given a lot of military-based vehicle-to-vehicle communication antennas for the electronic warfare. Those antennas are helped in the Kargil war. As well as there is an antenna research center at Theorem College of Engineering, Madurai. They are producing almost around 30% of the antennas used by the BSNL for their base stations with the Redamo. They are manufacturing and they are testing. I did my antenna testing in Theorem College of Engineering, Madurai. And you know, Samir centers in Calcutta, Samir centers in Chennai, Mumbai, Tata Research Center, Pune, CERI, Center for Electrical and Electronics Research Institute at Pilani. It is very close to my institution, Birla Institute of Technology at Pilani. So we did many antennas over there, and they are guiding us to fabricate industrial-like antennas, that is industrial manufactured antennas like quality. And you know, ISRO, IIST, Indian Institute of Space Technology at Trivandrum, they are manufacturing, they have their own unit, they are manufacturing all their antennas for ISRO, for their satellites and their stations. So there are a lot of things, sir. Only thing the students and staff get motivated. Since I did my PhD in the year 2007 to 12, during that time I have utilized almost 11 to 12 government and semi-government agencies, and we have developed most of the papers, our papers from there only, sir.
Okay, thank you.
So it is only thing is we have to travel, we have to spend money.
Yes.
We have to get the equipment. 5 times, 10 times they can allow to test free testing. If you keep on testing your antennas, fabricating weekly 2 antennas, 3 antennas, the problem is test and measurement unit is to be strongly collaborated with some of the companies. Now this L&T, Wipro, then those companies, Keysight, they are all ready to sponsor to the institutions those who are really fabricating antennas.
Yes, sir, it's true. I think students, only less number of students only going towards the antenna field when compared with other fields. So that's why
due to the mathematical models, sir, it involves lot of mathematics and analysis. Even for designing a simple microstrip antenna, you have to study at least 4 or 5 books. And effective antenna design, it is not such a easy to go through the mathematical models. But we can motivate the students. I never give projects in other fields. As my field is electromag antenna, I'm giving my projects to my UG and PG students only this field. They did wonders, sir. Few of my students are working in US, few of my students are working in Australia, Canada with this antenna division, and some are in ISRO also. So I'm so proud of them, sir. Really, they helped me a lot to learn many things from them also. Nowadays, antenna design, we are using this artificial intelligence also for optimization. You know this 5G toolbox. There is in MATLAB, we have 5G toolbox. If students are there, or staff members also, we can go through that thing. They are giving 6 month full trial for us.
So we can check. Yes, sir. Yeah, in our college also we got the MATLAB campus-wide license. Is it possible to use the toolbox through that?
Yes, sir. Yes, sir. 5G toolbox. You can ask your vendor. You can ask your service provider. Definitely, you can able to do that, sir. It allows us database management, artificial intelligence, everything, and you can collaborate with the leading institutions also in online with that 5G toolbox.
Okay, fine. I think next question is for you only. What inspired you to choose this field?
My marks in electromagnetics in my UG. I got very less mark compared with other courses. I scored 91 in engineering mathematics 3 in third semester of ECE. We have electromagnetics in third semester itself. I secured only 58 marks in electromagnetics. So I wanted to really study what is there, why I got less mark. Even I got 96 in DSP, digital signal processing. So I'm sorry to share this information, but I'm very good student, but my mark is so much reduced in electromag. So I want to learn it. So that time we don't have any local author book. We have started to study from William Haight, Engineering Electromagnetics by William Haight.
Yes, sir. Yes.
And you know, there is one book called Principles of Electromagnetics by Matthew O. Sadiku.
Yes.
So when we study the first chapter, the preface and the first chapter, they have given a lot of motivation for a beginner, the practical applications of this electromagnetics. So I have started choosing this field from BITS planning through my supervisor, Dr. Hema Singh. Now she is working as a scientist in the NAL, National Aerospace Limited, Bangalore. She is the motivator to choose this field. At that time itself, we have designed antennas for millimeter wave applications, not for 5G. We have designed antennas for millimeter wave applications for biosignal processing, biomedical applications. So she is one of the motivator, and my supervisor in my PhD, Dr. K. Shankar Kumar, he has K.R. Shankar Kumar, he is from IAC Bangalore. He did his full-time PhD in IAC in CDMA antennas. So he is another motivator to do my PhD in this particular 5G techniques. So in the year 2007, 6-7 itself, we have started to design antennas for this 5G. And we have around 3 patents during 2013-14.
Thank you, sir. Thank you. Very inspiring about you. Thank you so much, sir. Any more questions? Students, participants, conference presenters, any more questions?
It is not such a tough field, Dr. Devanayagam.
Yes, sir. Yes, sir.
It is not such a field. You can talk with it. You can bring Dr. Raghavan once to your institution.
Yes, sir.
To give motivation about this particular topic. He will do a nice motivation. He is one of the motivators. He used to attend many programs at Tyagaraja College.
Yeah, you know, he came already. He came once for our faculty development program in our college.
You know, Dr. Abhay Kumar, Ms. Raju, they are all the real pillars in this antenna field. Dr. Girish Kumar, Dr. Anamanda Rao from H. Rao, from Samir Center. Then you can even Mr. Dr. Belanis, you can send mail to Belanis. You know the book Antenna Theory. He used to reply to us within 3 working days.
Oh, okay, fine, sir.
And you know this, the Theodore Rappaport. There is one book written. He's from New York University. He's also very keen to help the students if your work is really good. So we used to contact them. We used to send emails. He replied to our mails, and he will nicely reply with some documentation, some research which is going with their laboratories. Even Belen is now also you can contact. I don't think so how he is going to reply, but previously in the year 2005, 6, 7 and we used to touch with Dr. Girish Kumar. He is also very polite and keen interest to help the students. Once we visit IIT Bombay, just visit Dr. Girish Kumar.
Sure. We'll follow, sir. Thank you, sir. Yes, sir. I think it's more than 1 hour. We can close our session. Is it okay, sir? Is there any more thing? Okay, fine, sir. Okay. So thank you very much for sharing your deep knowledge about 5G channel models and its advantages, challenges, everything, sir. Yes, now I would like to take the opportunity to invite Ms. A. Balakritika to propose the vote of thanks formally.
Good afternoon to one and all present here. It's my privilege to propose the vote of thanks to this August gathering on the International Conference on Smart Technologies and Applications, ICSTA 2022. First and foremost, I wish to express my sincere gratitude to Dr. Gunasekharan Thangavel for his presence. Thank you, sir, for addressing the audience. Through your guest lecture, we gained more knowledge about MIMO channel models and RF design challenges. With deep reverence, I thank our principal, Dr. L. Ganeshan, for making this wonderful assimilation, and special thanks for your laborious effort and your great generosity for permitting this international conference. Thank you, sir. And I intended to thank our Vice Principal, Sir, Dr. S. Rajakarunakaran, for his constant support for organizing this conference. Thank you, sir. Next, I extended my gratitude towards Dr. K. Vijay Lakshmi, Organizing Secretary for this international conference, who helped us in various ways to organizing this conference successfully. Thank you, My gratitude is also extended to Dr. S. Periyanagi, Head of the Department, Electronic and Communication Engineering, who constantly motivate us to conduct such events successfully. Thank you, ma'am. I also thank our faculty members for their tireless effort. Last but not least, my big thanks goes to all the participants for their active participation in this conference. Once again, I thank you all. Thank you.
Yes, sir. Thank you, sir. Thank you very much for your presence in your busy schedule. Thank you once again, sir. Thank you very much, sir.
Thank you so much for the patient listening and the nice interaction to everyone. Thank you for the opportunity. I thank Dr. Gunasekharan Perumal for his guidance and given me an opportunity to talk with this forum. So I wish the conference must go with great success. Thank you so much. Thank you. Have a nice day. Bye bye.
Thank you, sir. Thank you, definitely, sir. Thank you. So you can leave the session, sir. Thank you. Participants, kindly fill the feedback form which was posted in your chat box and get your certificates. Thank you.